Hello everyone and welcome back to another RL Education physics video. Today we're going to be looking at, again, projectile motion. This time we're going to be using energy though to solve our problems rather than constant acceleration equations. When we use constant acceleration equations, what we did is we took each direction, vertical and horizontal, separately and treated them by themselves. Now we're looking at energy. What we're instead going to do is take all the motion at once and then at the end separate the directions if we need to. So today's question, we're going to be analysing the speed of this ball here when it lands on the ground, assuming that it initially starts with 10 meters per second of velocity horizontally straight out here. It's 45 meters above the ground and g is 10 meters per second. Now, the first thing we're going to need to do about this problem is talk about what actually energy is and what our formulas are for it. So there are lots of different forms of energy that could possibly be held in one object at a time. However, for these projectile motion questions, all we're going to really need to consider are just two. We've got here UG equals mgh. This is the gravitational potential energy, and it's given by gravitational potential energy, UG equals mass times the strength of gravity times the height that it is above the ground. This is how much energy the ball could potentially have if it was to be pulled back to the ground by the force of gravity. Secondly, here we've got kinetic energy. Kinetic energy, or EK, is just given by half mv squared, so it depends on the mass of the object and then the square of how fast it's traveling. In all idealized circumstances where no energy is being lost due to friction or to heat or other forces like this, we have what's called the conservation of energy, which is that all energy will always be conserved. It can only change forms. So what this means for us is that if we add up all of our energy sources, gravitational potential energy, kinetic energy, if you have harder problems, they may involve a couple more energies. If we add up all of our energy sources and we get the total energy, that total energy will stay the same throughout our entire problem, no matter what changes are happening to our object. So what we're going to be doing is we're going to be finding our gravitational potential energy, finding our kinetic energy, taking this to be our total energy, moving to a different point, and then re-evaluating them, hoping to use what we found initially at the end. So if we look back at our initial problem here, we see we've got this ball, it's 45 meters above the ground. We know that potential energy is given by UG equals mgh. Now, for this ball, we're also going to take the mass to be 10 kilograms, which means, subbing into this equation, the potential energy we have in this scenario is 10 for mass times 10 for gravity times 45 for h. Luckily, seeing as we're just timesing by 10, we can just take this 45, add a 0 to it for this 10, add a 0 to it for this 10. This gives us 4,500. Now, put the units on this. It's an energy, so that means the units must be joules. Now, the second energy we need is going to be the kinetic energy. From before, we know that EK, or kinetic energy, equals half mv squared. And so in this case, that's going to be half of the mass, which is 10, times v squared, which is 10 squared, so 100. So we've got 100 times 10, which is 1,000, and then we've got half of that, so 500. Again, as this is an energy, all going to be in joules. So, important thing to note at this point is that our total energy is only made up of these two energies. Therefore, our total energy is just going to be 4,500 plus 500 joules, or 5,000 joules. This is the crucial value for this problem. This, because we're not dealing with wind resistance, because we're not dealing with any energy losses due to heat, due to sound, any of this stuff, will remain the same throughout the entire problem. So we now know that our total energy is 5,000 for every point during this ball's motion. We'll put that up the top here so we can refer to it if necessary. Okay, so the ball's general motion here is going to look like this. It starts out moving off directly to the right, and then gravity starts to accelerate it downwards, and it's going to curve towards the ground. What we want to find is the speed of the ball at this point here when it impacts the ground. So, what we're going to do is we're going to assess the two energies at that point, the gravitational potential energy and the kinetic energy. Okay, so when the ball is in this position, we don't know its kinetic energy, that's what we want to find out. However, we do know its gravitational potential energy. So gravitational potential energy, again, equals mg h. However, at this point, its height above the ground, when it's hitting the ground, is going to be 0. So, h equals 0 in this case, which means that the entire gravitational potential energy is just going to be 0. Now, we know from earlier that the total energy is still going to remain 5,000 joules. So, if we're only dealing with gravitational potential energy and kinetic energy in this problem, that means that all 5,000 of these joules have to be in the kinetic energy. So we simply write kinetic energy equals 5,000 joules. Now, we also know that the formula for kinetic energy is EK equals a half mv squared. What we really want to find is the speed v, so we can just rearrange this to get it. So now all we have to do is move things around. We've got a half here, so if we times both sides by 2, that'll get rid of that. 5,000 times 2 will be 10,000, which now just equals mv squared. And we know from before, 10 kilograms, so this is now 10 v squared. Once we've done this, divide the 10 across, we go from 10,000 to 1,000. Equals v squared. Square root both sides gives us the square root of 1,000 equals v. At this point, you can retreat to your calculator and find out that the square root of 1,000 is approximately equal to 31.6 meters per second. And so the speed of this ball when it hits the ground is going to be 31.6 meters per second, and it's going to be in some kind of diagonally downwards direction. Problem for us now, potentially, is that we don't know how fast it's moving downwards, how fast it's moving across. However, we can solve this pretty simply. We know, from just thinking about the problem logically, that the ball is going to follow some path like this. It's being accelerated downwards. It starts with horizontal velocity. However, we also know that because we're not dealing with air resistance, because we're not dealing with any other accelerating forces, this horizontal velocity will never be affected by the downwards force of gravity. Therefore, at the end of its motion, we have a velocity that goes out in this direction, approximately, and then we can break this down, just like we did last week, into a vertical component and into a horizontal component. Now, the great thing about doing this is that we already know what the horizontal component is. As we just said, this 10 meters per second is never affected by gravity or any other forces in this instance. So it's 10 at the start. It'll still be 10 at the end. So this here is 10. We also know from the problem we just did that its actual speed, its overall speed, is approximately 31.6 meters per second. The only thing we don't know is this downward speed here, x. So we can find that out by just solving this Pythagorean triangle, like you have hopefully done many times in maths. Quickly running through that, we know that, okay, x squared plus 10 squared is going to have to equal 31.6 squared. Rearrange this, minusing the 10 squared across, we get x squared equals 31.6 squared minus 10 squared. Take the square root of both sides. X equals square root. Okay, technically it should be plus or minus, but I'm going to leave that out for time's sake. We know here that this is a positive direction. We've already decided which direction this is in. We know it's downwards. 31.6 squared minus 10 squared. Shoving this straight into our calculator, we just get x to be equal to approximately 30 meters per second. And so hopefully you can see with this problem, we've managed to take the energy that the ball initially started with, know that it must maintain that energy throughout its entire motion. Then, when it gets to the bottom here, recalculate its kinetic energy based on its new gravitational potential energy, use that to find its overall speed. And once we had that, we could find all of the different components of velocity just like we had last week. We have this horizontal component of 10, we have this vertical component of 30, and we also have now its overall speed, which is 31.6 meters per second. For your homework question this week, we've got a ball, 10 kilos again g, 10 meters per second. However, it's moving off at 13 meters per second, an awkward number, at an awkward angle of 17 degrees, and it's got to fall an awkward distance of 67 meters. Hopefully, what you'll see when you try these questions, finding the speed of the ball when it hits the ground, and then finding the horizontal velocity and the vertical velocity, is that this method allows us to deal with these weird numbers quite easily. Whereas with the other method, we get a horrible quadratic. Here it should come out nicely. Best of luck.